Hello everyone, I am ALIAS George from APATCH. Today we will be discussing about clamping circuits from the very basics of diode and capacitor to some of the examples of clamping circuits. So we can just look into the other names of clamping circuits. It is also known as DC restorers, clamped capacitors, diode clamper circuits, and also AC level shifter or just level shifter. These all names are possible for clamping circuits. So what mean by clamping circuits? We can just take an example and start studying clamping circuits. Suppose if our input waveform is just a sin x like this curve, so if we are adding 2, we can see that we can see that it just shifted upwards. Or if we add -2, we can see that just shifted downwards. So what we are doing now means we are adding positive or negative DC voltage to our input waveform, so that our original input waveform will get shifted upward or downward depending upon our use. So this clamping circuit is used for shifting the input waveform either upward or downward without affecting the input waveform in any manner. So we can see that there is no shape change for the input waveform. The peak to peak voltage remains same and the RMS value remains same. Everything remains same. Only there is a level shifting. Depending upon the DC voltage we are applying, we can shift upwards or downward. If the input signal is shifted above upward, we can say that it is a positive clamping. If it is negative side means negative clamping. So these are all written here. They are used to shift the input waveform to a level by adding a positive or negative DC component to the input wave so that it will be pushed to either positive. If positive means positive clamper or negative side, then negative clamper. Same explanation, you can just read it. And one of the inference we got from that graph is that our input waveform will remains the same even after shifting. There will not be any changes in the peak to peak or the RMS value of the input waveform while clamping. And the components needed to achieve this clamping is capacitor, diode, a resistor and a voltage source if necessary for the additional shift. These all are the very basic about clamping circuits. Then as I earlier told, we will be starting from the very basics of whatever the components used in the circuit. So first we will be looking into diode. So we can see here that a diode has two cathode and anode, and if the diode for the time being assume this diode to be ideal, if the anode of the cathode is more positive than the cathode, then we can say that the diode is forward biased. If it is ideal, we can just say it is short circuited. If the anode is less positive than the cathode, the diode is reverse biased, or we can say it is an open circuit. So just it behaves as a switch. If anode is more positive than cathode, it is a closed switch. If it is in the reverse direction, anode is less positive than the cathode, or cathode is more positive than the anode, it is just an open circuit. This is all about diode, very basics of diode. So let's read it. Next, the component used in the clamping circuit is capacitor. So we will be looking into that. So these all are the capacitors. As we all know, when we apply voltage across the capacitor, we can apply the voltage in two manners. Either just applying to a capacitor or through a resistor in series. These two ways are possible. So we will be looking into that two cases, and the right side here written is through a resistor case. As we all know, this is the charging equation. Voltage across will be, this is the maximum voltage of the source we are applying into 1 minus e raised to minus t by RC. While discharging, this is the equation. These all are the equations when charging the capacitor through a resistor. So first we can look into charging without a resistor. In order to explain this, I will be using Tinkercad, so you can easily note that what is happening here. So here I took a polarized capacitor, power supply of 10 volt, and a multimeter of voltage reading, and a DP DT switch. We can start simulation. As we on the switch, so you can look here, I switch off the switch, and while at the moment I am on the switch, it will get 10. Just look again, it will get 10. With the fraction of a second, the capacitor will be gaining the voltage of the voltage source. So there is no time delay for achieving that. This is the case without the resistor. You can see here I have not used any of the resistors. So we can conclude, means if there is no resistor, the capacitor will attain the voltage of the voltage source within the very fraction of seconds. So the next case is charging or discharging with the resistor in series. So the right side written equations is valid for that case, and we will be also using Tinkercad for this explaining that also. We can see here voltage source is the multimeter, a polarized capacitor. I have used an idea. In this circuit, the capacitor will be discharging through this resistor and charging through this resistor. So we can start simulation. So this is the switch for charging, and this is the switch for discharging. Okay. So you can see that here the capacitor is charging through a resistor. This is the charging resistor, and it is of 170 ohms. and this is the discharging resistor. It is of 1000 kilo ohm. So we can start simulation and switch on the charging resistor. So you can see that, as I earlier told, without resistor case it takes some it will, at the moment we are switch on the switch, it will attains the 10 volt, but here it took some time for attaining that 10 volt. That is achieved by connecting a resistor in series with that connection. This is the case, a resistor in series while charging the capacitor. I turn off the switch and switch on this discharging switch. You can see earlier while charging it was somewhat speedy, somewhat charged in a speedy manner, but now when I turn on the discharging switch, you can see that it is very much slow in rate. That is because the discharging resistor value, you can see that the difference only here in the charging and discharging resistor. Discharging resistor has the 1000 kilo ohms, but charging resistor is just 170 ohms. Or if I will add one more case, we can increase this charging resistor value to 1000 kilo ohm and see what happens. So you can see that it is starting from millivolt. So it is charging in the very slow rate. As earlier, if we change this resistor value to 170 ohms, so you can see that this is easily attaining 10 volt. So the idea that to be retained from this illustration is that if we increasing the RC constant, here capacitor is not changing, resistor only changing. If we increase the RC constant for charging or discharging, we can increase the time for that purpose also. If I increase the RC constant of the charging circuit, then the charging will be takes place in a much slower rate, as similar for the discharging case also. This is what I need to be explained to you all. Charging without resistor and charging with a resistor in series. I hope everyone understood this. So we can move into next case, time constant. What is a time constant? Time constant is just the product of R and C, and time constant is the time required to attain 63% of the maximum voltage that we applied. As just this is the basic explanation for the time constant. In the previous illustration we have seen that for the charging case, if we increase the RC constant, we can increase the duration for that charging. Similar in the case of discharging, if we increase the RC constant, the discharging duration is we can make it longer and longer by increasing RC constant. This is the idea you need to get from this slide. So explain this all. Next concept is that we have gone through all the basics of the capacitor, and what is important in the case of clamping circuit, we will be connecting this capacitor to our clamping circuit. In order for our clamping circuit to work very perfectly, there is one very basic condition that RC constant should be greater than 10 times of the time period of the input signal. In our next example, all the examples of the clamping circuit will be following this basic law. Basic law, I will be explaining what if it is less than 10 times t. I will be explaining in the next slide. For now, you just trust RC constant should be greater than 10 times to get a perfect output in the case of clamping circuits. But you all now know that the use of RC constant, by varying the RC constant, we can vary the duration. We can increase the duration if we increase RC. That is the use of RC. Next, we can see, before going to the next slide, I want to explain one more thing. This is the equation for discharging of a capacitor through resistor. You can see here a simple example. I am taking the maximum input voltage equal to 6 e power minus t by 1. Now I am taking the RC constant minus t by RC, right? So RC to be 1, our time constant to be 1. In the next example, I am increasing the RC. If I put it 10, you can see that earlier it was just this. This is the pattern in which the capacitor is discharging. So you can see that if 6 is the maximum voltage, it is decreasing very drastically. But if we increase our capacitor RC to a higher value, we can see that it is decreasing in a slower rate. And one more thing we can add here is that we can say that for a small time interval, suppose assume 0 to 1 here, we can say that it remains as 6. It is remaining 6 here, 6, right? So if we increase the RC constant for the small time interval, we can say that capacitor will provide same constant voltage. That is what I need to be explained through these diagrams. If we again further increase the RC to a higher value, then we can very much say that for a smaller time interval, the capacitor will provide a constant voltage if we increase the RC time constant for discharging. Okay. So we will be continuing now. So please keep in mind this. It is very important in the case of clamping circuits. What if the RC product is less than 10 times time period of the input signal? Earlier we talked it is very much necessary to get a perfect shape. Now we can see what if it is less than 10. We can infer that. You can see here left side it is a long time constant and short time constant. In the previous wave illustration, you can see I have explained that if the RC constant is very long, RC constant is very much higher value, the capacitor will provide a constant voltage for short time interval. This is what here it is shown for a long time constant. But what if it is a short time constant? Then the capacitor will not provide the constant voltage. It will provide the voltage will be varying, will be drastically lowering. So we will get a distorted shape if the time constant is short. That is why we are saying in the case of the clamper circuit, to get a very perfect output waveform, the RC constant should be very much 10 times greater than the time period, 10 times the time period of the input signal. In the next, this is what written here, you can read it. So here we will be discussing starting some of the examples for clamper circuit. It is very easy. We can see in this, we can see this first here. I will explain, try to explain this. You can see it.
Positive clamper without biasing. It is positive clamper. Okay. I will draw the circuit of that in the very first, very easy circuit. So this is our V output. That is the voltage across this resistor, capacitor, diode, and here we supply our input voltage in this manner. For the time being, assume that voltage across the capacitor is Vc and this voltage, output voltage, is of this side. And assume that we apply the input voltage as a sine wave. See a sine wave of maximum out amplitude Vm. Okay. And here there is in the circuit there is no battery. We are keeping that for reference. So it is known as without biasing. And it is a positive clamper. So the output waveform should be shifted upwards. Okay. We can say that there is two cycle for the input, positive and negative cycle. And during the positive cycle, the diode will not conduct. So we can easily subdivide this circuit into two cases. There is diode on condition, diode off condition. This is when during the positive cycle, and this is when during the negative cycle. Okay. If the diode is on, it means it is short circuited. We can copy this. Sorry. So this is the two cases. So we will be only getting this only. What if the diode conducts? What is diode is on for this case? If the diode is on, it will be short circuited, which means the diode is removed and a straight wire is connected, which effectively means that we are connecting this straight wire across this resistor. So the resistor is also short circuited. We can remove this resistor. Since there is this two potential here and here, this same at the same potential, V output will be 0. Please keep in mind. And for the diode off condition, that is during the positive cycle, the diode is off, that means it is open circuited. We can remove this diode if it is open circuited, which means this circuit. We can apply the KVL in these two conditions. First, we can apply KVL in this off condition and see what is going on. V in minus Vc minus V out equal to 0. So keep it that. And the second case, we are applying in this manner. So minus V in plus Vc equal to 0. So Vc equal to V in. As the capacitor, we can see that capacitor is charging in the case of a negative cycle. And there is no resistor also in series, which means capacitor will easily attain the input voltage supply. This is happening during the negative cycle and the capacitor will be charged to the maximum value of V maximum. And the next case is capacitor is discharging through a resistor and the RC time constant of this discharging is very high. So for the small time interval, we can say that capacitor provides a constant voltage, that is Vm. So V output is nothing but V in minus Vc. During the positive cycle, it will provide constant voltage since the RC time constant is very large. So it is V in minus Vm. Sorry. Okay. Minus Vm. Now here it is Vc equal to minus V in minus Vm. Here it is minus Vm, okay. As Vc equal to V in itself, but capacitor will be charged to a negative. During the negative cycle, capacitor will be charged to a negative value. So Vc equal to minus Vm. As we are substituting here, for Vc we are minus Vm. So it will be plus Vm, okay, sorry. Please keep in mind, V out is V in plus Vm. Using this equation, we are plotting our output waveform. Here the input waveform value is 0. What if the input is 0? Output will be Vm. So it is here. What if the input voltage is Vm here? Then it will be 2Vm. It will be 0. It will be here. So it will be following this way, shifted way. So you can see that the input waveform is shifted upward by a value Vm. So the DC value, the DC component we have set into, or we have clamped that DC Vm DC component into the input wave component. Since it is shifted to the positive side, it is known as the positive clamper. I will go through it again. Here there are two cases during the positive cycle and negative cycle. During the positive cycle, diode is off, and during the negative cycle, diode is on. During the negative cycle, charging of the capacitor will take place. During the positive cycle, discharging will take place through a resistor. Please note, RC value is very high, so the discharging will take place in a very slow manner for a small time interval, we can say that capacitor will provide a constant voltage. So we have took it as Vm. From that we get the equation for V out, that is nothing but V in plus Vm. Using that equation, we plot our output waveform. So the result is it is shifted upward by a value of Vm. That is all for that.
I hope that explanation for this is very much useful. Everyone understood that, I think. And next, this is what I told. Please read it. During the negative half cycle, capacitor charges up to Vm. Here it is, I mentioned Vm. Actually, when we consider the sign, it is minus Vm, but the value is Vm. Because of the high time constant, capacitor produces a constant voltage before next negative half cycle. So it is a capacitor is charging during the negative half cycle, and during the positive half cycle it provides a constant output voltage, that is Vm. Before next, then the next half cycle it will again charges to Vm. During the positive cycle it provides a constant voltage, then again charges. This is the manner in which capacitor is acting in this circuit, and we given the output waveform equation also. I hope everyone understood this. If not, please rewind this video. Next, we are going to negative clamper without biasing, negative clamper, which means the output waveform will be shifted downwards. Okay, so we will be explaining this.
We are going to explain negative clamper without biasing. It's negative clamper and the battery also not included. I will soon very speed I will draw the circuit. Nothing is there. To the previous example, we are just reversing the diode and remaining everything as same. This is the output we taken across the resistor. Okay, and this is the input we supplied. For the time being, let's assume that voltage across the capacitor follows this like, and the output is here. This is the resistor. This is our circuit. Here also, the input waveform is a sine wave. Of the peak value Vm minus Vm. I have drawn it very badly, okay? Sorry. We can divide this case as I earlier told similarly. Similar approach, not same approach I am using. Diode on condition, diode off condition. Here we can easily say that when the diode will on during the positive cycle. Okay. And the diode will off during the negative cycle. Okay. Now we need to, the next step is we usually follow. We need to place the circuit. Place the circuit. Okay. You can drop that, these two things. Okay. So what if the diode is on? Diode on means diode is short circuited, which means we can remove this diode and short circuit this, which effectively means resistor is also short circuited. We can remove this. So the output voltage will be 0. Since these two points here, this point and this point, voltage difference is 0, Vout is 0. Okay. And during the negative cycle, here in the left case, the diode is off, which means it is open circuited. We can just remove this diode. And while applying the KVL, in this case, I am applying in this direction and this direction here. So in the right, we can say that minus Vn plus Vc equal to 0, or you can say Vc equal to Vn. Here in this case, please note that diode is on for positive cycle. So that capacitor is charging in the positive cycle, not in the negative cycle as earlier told. It is charging in the positive cycle only. So since it is charging in the positive cycle, the capacitor will gain, here this cycle it is charging, capacitor will gain the maximum value of Vm. It will be charged to Vm, then discharging happens. Okay, first we can think about charging. It will attain the maximum value of plus Vm in this case, because the capacitor is charging in the positive cycle, so it will be charged into the plus Vm. In the left case, we can apply the KVL and plus V in minus Vc minus V out equal to 0, or V out equal to V in minus Vc or V in minus Vm. This is the equation for the output waveform. This is the equation. So we can plot the output waveform using this equation. So we can start from the 0. At 0, it is minus Vm. Using this equation, it is minus Vm. And at Vm, it is 0. At minus Vm, it is minus 2 Vm. So it will follow this path. Here it is minus 2 Vm. That is the result of this negative clamper. As the name suggests, we can see that the input waveform is shifted to the negative side below the center axis. That is why the negative clamper. I will explain one more time. There is two cases. The difference from the positive clamper is that it is charging, the capacitor is charging in the positive cycle here. But in that case, it is charging in the negative cycle. But in this case, positive cycle, capacitor is charging. So it will be charged to positive cycle plus Vm, that is the maximum voltage. And during that charging condition, there is no resistor. So it will easily attain that voltage. But in the discharging case, once it gets charged, next discharging happens. The very basic condition is RC time constant should be very large. So once it gets charged, the discharging happens very slow manner. So once happen charge, it will be charged to Vm. So we can say that it provide a constant voltage for the small time interval after charging. That is Vm. First charging to Vm, then provide constant voltage. Then after again charging to Vm, then the constant voltage. In that way it moves. And we have got the output wave equation. Using that we plot it and we observed that the input waveform is shifted downwards. That is all about negative clamper. Okay, thank you.
And this is what here happening here. Uh, So during the positive half cycle, capacitor charged to VM, and because of the high time constant, it provides a constant voltage to the next positive half cycle. And during the positive cycle, this is the output waveform, output wave equation. Using that, we plotted that, and we observe that this is the input sine wave, and this is the output. Here we can see that there is a shift to down, and we have clamped the VM to this input waveform, so it get shifted downwards. That is what negative clamper without biasing. Okay. Next, we can see positive clamper with positive biasing. Earlier there was not biasing. Now onwards we can see what if there is a biasing or an external battery is provided with the diode.
Positive clamper with the biasing, that is positive biasing. We can very fastly draw the circuit. Here it is positive biasing. This is our resistor and this is our V out. For the time being, assume VC is the and this is also, here it is V in. Let it be that. And the reference battery, that is VB, positive here, negative here. So we can ground this. And we can say that it is VB here. And let assume that we are supplying a sine wave as the input wave of amplitude Vm minus Vm, and our let the VB be somewhat below Vm, here V, okay, minus VB. We can subdivide this case as two. Basically we are following the same rule. Diode conducting case, that is on case, and diode off case. Here diode will on if this potential, here potential value is less than VB, that is V in less than VB. This case the diode will be on. Balance all other cases diode will be off. In this graph, if it is less than VB, which means all this part diode will be conducting this part. Okay. So we can say that the maximum value in the conducting part is in the negative side. So the capacitor will be charged during the negative cycle. Okay. We can, let's copy this circuit. Paste it here. Okay. Stop this. Okay. When the diode is on, it means it is short circuited. We can remove this diode and place a single wire here. Sorry. Place a single wire here. And when the diode is off, it is open circuited. We can just remove this all. There is no use with single battery with one terminal connected. So we can remove the battery too. And similarly, the same approach is we are just applying KVL in this loop and this loop. and we'll be writing the equations. V in minus Vc minus V out equal to 0. V out equal to V in minus Vc. Here in this case, during the negative cycle, capacitor will be charged to maximum value, that is minus Vm. So minus V in plus Vb plus Vc equal to 0, or Vc equal to V in minus Vb. Vc max equal to, it will be charged to minus Vm minus Vb. By substituting here, V0 equal to V in plus Vm plus Vb. This is the final wave out equations. This is the output wave equation. When we can plot this output equation, so when the input voltage is equal to 0, the output is Vm plus Vb. So it will be somewhat like here, in this position, Vm plus Vb. So it will be here. When the output is Vm, it will be 2Vm plus Vb. That will be a thing above this position. We can redraw this, and it will be like this. This will be our wave equation, output wave. So we can see that the input is shifted output by a value of Vm plus Vb in this case. If we applied a, or what is the use, what is happening here? If we apply a reference battery in the positive biasing, we can shift the input to a desired value by varying the Vb. So if it is like Vm plus Vb, right? So if we apply Vm to here, then the input can be shifted to 2Vm. Or instead of Vb, we can apply 2Vm, then the wave will be shifted to 3Vm. So as per our desire and requirement, we can shift to whatever the value. That is the use of biasing. That is, here it is positive biasing. Next case is, what if it is a negative bias? So all the conditions remain as such, there is no change, only we are changing the direction of the battery. So in the output wave, what will be there? What is the change there? The output wave will be, so I am writing here. So for negative bias, V out equal to Vi, here it is written, plus Vm. Instead of plus Vb, there will be minus Vb. That is only change from here. Only we are changing the direction of Vb. Okay. So if we plot that to the in our waveform, it will be somewhat like this. Yeah. So this is but positive biasing and a negative biasing. Both has equal use. Okay. That's all.
So here it is positive number with positive biasing. So during the negative half cycle, capacitor will be charged to minus Vm minus Vb, as we told. And because of the high time constant, capacitor provides a constant voltage before the next negative cycle. When before it gets again charging, it provides a constant voltage in between charging conditions. And this is the output wave equation. So there is a positive shift there. There is a positive shift, so it is a positive number, and we can see that positive biasing is there. Positive biasing and a positive shift. And next, there is positive clamper with a negative biasing. Here we also discussed this case. There is only one change, Vb we are changing, all other cases remain as such. So we are just reversing. Instead of minus Vb, here we are giving plus Vb. Balance all other conditions same. So the output wave equation will be minus VB instead of plus VB minus VB. That is all here. So using this case, the input waveform will be shifted to Vm minus Vb. But positive bias means Vm plus Vb. Here Vm minus Vb. Next, we are going to explain negative clamper with the positive biasing, including we will be explaining with the negative biasing also. So we can see
negative clamper with the positive biasing. So we can draw the circuit. This is our V in. So it is a positive bias. So we are providing the VB battery in this manner, and this is our resistor. This is the V out. Okay. We are grounding this. Here the potential will be VB, and this is Vn, and this is our capacitor. And the next approach is we are providing here a sine wave as an input of amplitude Vm, and here we will be dividing this two again into two cases: diode on condition, diode off condition. We can easily say that diode is on for V input is greater than VB. Diode will on for that particular instance. Here in this graph, this is VB and minus VB. For that particular time, diode will on this time. Okay, we can copy our circuit. Okay, so one more thing. Okay, you can place the here, place here. It's more accurate. You can drop all the other things. And when the diode is on, we can say the diode is short circuited. So we can remove this diode and connect a straight wire. And when the diode is off, we can remove this diode and it is open circuited. So we can also remove this battery too. And applying the KVL in both these circuits. So in this manner here, we can just write down the KVL equations. V in, assume that it is Vc here plus minus, here also Vc minus plus minus, okay, minus Vc minus V out equal to 0. So V out in fact equal to V in minus Vc, and here the capacitor is, we can see that the above this condition capacitor is charging when the V in is greater than Vb, or we can say this charging is happening during the positive cycle. And during the positive cycle, the maximum voltage to which capacitor is charged is Vm, right? Yes. So we can apply the KVL equations and minus V in, this is V in only, plus Vb equal plus Vc equal to 0, or Vc equal to V in minus Vb. It is maximum of this is Vm minus Vb. We can supply this to this equation. V0 equal V output equal to V in minus Vm uh, plus VB. This is what we are getting. Okay, so please note this equation. We can draw the output waveform using that equation. So when the input is 0, the output is minus Vm plus Vb. Minus Vm plus Vb will be somewhat here. It is somewhat, it will be here. So it will be the starting point. Just here, okay. Minus Vm plus Vb. Then if the Vm is if the V in is Vm, then the output is Vb. Sorry guys, there is some problem. Okay, we can drop that. This is minus Vb, and somewhat here we can note our minus Vb. Then it will be, if the V in is Vm, then it will be Vb only. Vb here, sorry, it is here. So it will be shifted in this manner. Okay, you can try this. You can see the relative to the input voltage, the output voltage is shifted to a value here. It is minus Vm plus Vb for the case of positive biasing. And what if for negative biasing? We can just replace that Vb in the reverse direction. So the output voltage equal to V in minus Vm minus Vb. That will be somewhat again down with respect to this one. It will goes again down here somewhat here. It will be starting from here only. This manner it will be shifted. So for positive biasing, output wave equation is this one. And for negative biasing, just instead of Vb minus Vb, this will be the output wave equation. Here in this negative clamper, capacitor is charging to its peak value during the positive cycle. For the positive clamper, it is happening in the negative cycle. That is a difference. Okay, please note that too.
During the positive half cycle, capacitor charges up to plus Va minus Vb, and up to the next half cycle, the capacitor will be providing constant voltage. Once it gets charges to Vm plus minus Vb, it will provide constant voltage, then again charges constant voltage. As manner it will be providing. Then the output wave equation is mentioned here. It is for a positive biasing, please note that. And what if it is a negative biasing? Then instead of Vm minus Vb, it will be Vm plus Vb, and the output wave equation is Vi minus Vm minus Vb. That is only the difference. Instead of plus Vm minus Vb. Okay. So in these conditions, negative clamper, we can see that output waveform is shifted to the negative side. Okay. And till now we have discussed about sine wave only, and these are the some examples for square wave, and you can try this to whatever principles I shown. The same principle you can apply here also and get these outputs. So this is all about clamping circuits. I hope I all understood this, and I have tried my maximum to include all the illustrations from Tinkercad and etc. And this all figures I took from different sites. So thanks for all their owners and sites. I think and you enjoyed my lecture. I think I was able to hand over all the ideas. So please try this. Thank you. Thank you.